In this video, I'm going to demonstrate how to solve a problem that is similar to the problem set for Chapter 13. The problem says that the thermal diffusivity for a particular soil is 0.57 times 10 to the minus 6 meters squared per second. Part A says to calculate the damping depth for the diurnal or daily temperature waves. In order to do this, we need to use the equation given in the textbook for the damping depth. This equation says that the damping depth, d, is equal to the square root of the soil thermal diffusivity, alpha, multiplied by the period divided by pi. If we plug in the thermal diffusivity value that we're given, along with a 24-hour period, we get the following equation. Now notice before we move on that our units are not unified. So we have meters squared per second and a period of 24 hours. So before we move on, we need to convert this period from hours to seconds so that it matches the thermal diffusivity units that we're given. When we do this, we find that there are 86,400 seconds in one day. And now we can plug this value into the equation and solve for the damping depth. In this case, the damping depth is 0.125 meters, or considering two significant figures, 0.13 meters. Part B asks us to do the same calculation again, but instead of for a daily temperature wave, this time we're looking at an annual temperature wave. So again, we'll use the same damping depth equation, but this time, instead of plugging in 24 hours, our period is 365 days. Again, we have to unify the units here, so we need to convert 365 days to seconds, and when we do that, we find that there are 31,536,000 seconds in 1 year. Again, we can plug in this value into our damping depth equation, and we find that our final answer is 2.392 meters, or, again, considering two significant figures, 2.4 meters. So parts A and B demonstrate the difference in damping depth between the daily temperature cycle, which only penetrates 0.13 meters into the soil surface, versus the annual temperature wave, which penetrates down to 2.4 meters below the soil surface. Part C says, at what depth is the amplitude of the annual temperature wave only 5% of the amplitude of the annual wave at the surface? So this problem is asking us first to compare the amplitude of the annual temperature wave at some depth with the amplitude of the annual wave at the surface. In order to do this, we want to use the equation that allows us to calculate the soil temperature at any given depth and time. Now, in this equation, the term that determines the amplitude of the temperature wave is A0 multiplied by e raised to the minus z divided by d. So this is the term that we're interested in this equation. And what we want is to estimate the depth of the amplitude of the annual temperature wave when it's only 5% of the annual temperature wave at the surface. So here we're comparing, we have a ratio of the amplitude of a wave at some depth that we don't know, that we want to calculate, and this is divided by the amplitude of the temperature wave at, you see here, Z0. So this is the amplitude of the temperature wave at the soil surface. And we are interested in calculating the depth at which the ratio of these two amplitudes is equal to 0.05, or 5%. So first off, we can see that the A0 values here will cancel out, and we can also plug in our damping depth that we just calculated in the previous problem for the annual temperature wave. And when we do that, we have 0.05 is equal to e raised to the minus z divided by 2.392 meters. And here in the denominator we have e to the 0 power because we said in the denominator we are looking at the soil surface, so this z value is equal to 0. And further, we see that anything raised to the 0 power is equal to 1. So now our equation is simplified a little bit, and the only unknown value that we have now is this z value, which we need to solve for. This will tell us the depth at which the amplitude of the annual temperature wave is only 5% of what it is near the surface. In order to get rid of the e term, we need to multiply both sides by the natural log. When we do that, we find that minus 2.996 is equal to negative z divided by 2.392 meters. Now this equation is very simple, and we just need to solve for z by multiplying both sides by 2.392 meters. When you do this, you see that z is equal to 7.165 meters, or, again, considering two significant figures, 7.2 meters. Part D asks us what is the time lag between the occurrence of the daily maximum temperature at the surface and at the 30 centimeter depth. So realize here we've moved from an annual temperature wave back to a daily temperature wave. The equation that we want to use is the equation given in the textbook for estimating the time lag, where we have the time lag here, T2 minus T1, is equal to the difference in the two soil depths that we're looking at, divided by the square root of 4 pi times the soil thermal diffusivity divided by the period. So if we plug in the values that were given, we don't know the time lag. This is what we want to solve for. We know that the deeper soil depth, Z2, is 30 centimeters, and we know that the other depth, Z1, is the soil surface, or 0 centimeters. We plug in the soil thermal diffusivity that we were given, and we divide that by the period, which is 24 hours. But just like in parts A and B, we need to convert this period so that it matches the units of our soil thermal diffusivity. When we do that, we have a new period value of 86,400 seconds. And notice here that in order to allow the numerator and denominator to also have the same units, I've converted from centimeters to meters. You can easily solve this in your calculator, and when you do, you get an answer of 32,948 seconds. However, the question asks for the time lag in hours, so we need to convert this value in seconds to hours by dividing by 3,600 seconds. When we do this, we get a value of 9.15 hours, or 9.2 hours.